Hi everyone. Let's work on this problem where we're mixing solutions containing sodium phosphate and calcium nitrate. So in our first solution, we have 25.0 milliliters of 0.185 molar sodium phosphate. And we're going to mix that with our second solution, 34.0 milliliters of 0.140 molar calcium nitrate. And those are all going to get added into the same solution. I'm picturing a beaker, and I'm picturing, beaker number 3. Well, it has a total volume of 25 plus 34. That'll be 59.0 milliliters, and they want to know the concentration of each ion in the final solution. So that's this solution. In other words, the molarity equals what? And what are all the ions that we could have? Well, there could be sodium, there could be phosphate, there could be calcium, and there could be nitrate. So what are the molarities of these ions in the final solution? The first thing we ought to do is see if a reaction occurs between our two salts, the sodium phosphate and the calcium nitrate. So sodium phosphate is aqueous. It is reacting with calcium nitrate. That's also aqueous. And our first product is going to be sodium nitrate, and all group 1A salts are soluble and all nitrates are soluble, so that's aqueous. And our other product is going to be calcium phosphate, and phosphates are insoluble for the most part, so this is our precipitate. So a reaction does occur between these two salts. I'm glad we wrote out the equation. Let's balance it. I think I'm going to need 3 calciums on the left, and now I've made 6 nitrates on the left, so I better have 6 on the right. Now I've changed the sodium, so if I put a 2 here, I think the equation is balanced. So when I look closely at this equation, it looks like the only ions involved in the reaction are going to be calcium and phosphate. I bet sodium and nitrate are going to be spectators. Let's confirm that by writing the complete ionic. So that'll be 6 sodiums plus 2 phosphates and 3 calciums and 6 nitrates. On the right, 6 sodiums, 6 nitrates, and then we have our precipitate, and we'll just leave that alone. So yes, indeed, the spectators are sodium and nitrate. They did not participate in the reaction. Sodium simply got poured from beaker number 1 into beaker number 3. And nitrate likewise got poured from beaker number 2 into beaker number 3. In other words, those spectators, sodium and nitrate, just got diluted. Let's calculate their concentrations first, because I think that should be a little bit easier. So the spectators just got diluted. They did not participate in the reaction, they simply got diluted. So let's work on sodium. And be very careful when thinking about the concentration of sodium in beaker number 1. Is it really 0.185? No, because for every 1 mole of sodium phosphate, you have 3 moles of sodium, so you have to take the 0.185 and multiply by 3. And when I did it, I got 0.555 molar of sodium in beaker number 1. Now, what happened? You diluted from 25 to a total volume of 59. That's your dilution factor. And your milliliters cancel. When I did the arithmetic, I got 0.235 molar sodium. So that's one ion down. And maybe you're thinking to yourself, well, why don't we have to worry about the 6 sodiums in the balanced equation here? You don't have to worry about the coefficients in the balanced equation because sodium was a spectator. It did not participate in the reaction. You're only worried about how it got diluted from beaker number 1 into beaker number 3. And again, this formula is just C1 V1 equals C2 times V2. I've just taken that initial concentration, in other words, and multiplied by the dilution factor. Let's do the same thing for the other spectator, nitrate. And again, be very careful when writing down the concentration of nitrate in beaker number 2. Is it 0.140 molar? No, it's going to be twice that. So 0.280 molar nitrate got diluted from 34 milliliters to a total volume of 59. And I got 0.161 molar nitrate. That takes care of the spectators. What about the concentrations of the ions, calcium and phosphate, that actually participated in the reaction? That's a little bit harder, but let's give it a shot. So I've written the net ionic equation which shows the ions that participate in the reaction, and now I want to remind myself the concentrations of each ion and maybe the volumes of solution. So for phosphate, remember we had 25.0 milliliters and the concentration was 0.185 molar. And for calcium, we had 34 milliliters and the concentration was 0.140 molar calcium ion. So which reactant, phosphate or calcium, determines how much product I can get? Well, it's going to be the limiting reactant, so I've got to determine which one is the limiting reactant. So I'm going to try phosphate. Here again is my concentration of phosphate, 0.185 moles of phosphate for every liter of solution. And I have 25 mils, that's 0.0250 liters of solution. And remember, the way that I determine a limiting reactant is I ask myself which reactant gives less product. So for every 2 moles, here's where that 2 comes from. For every 2 moles of phosphate, I'm going to make 1 mole of precipitate. And I got 0.00231 moles of the precipitate if phosphate is the limiting reactant. I don't know yet because I still have to test calcium. So I'm going to rewrite the concentration of calcium as 0.140 moles of calcium for every liter of solution. And I have 34 mils, which is 0.0340 liters. And now I used my balanced chemical equation for every 3 moles of calcium, we make 1 mole of the precipitate. Okay, I think we discovered our limiting reactant. I get that 0.00159 moles of precipitate are formed, which is less than the moles of precipitate up here. So calcium is the limiting reactant and phosphate is the excess reactant. So since calcium is the limiting reactant, the concentration in the final solution, and by final solution, I mean this solution here, the concentration of calcium is 0 molar, and that's again because calcium is the limiting reactant. It gets used up in a reaction. So now all we have to do is get the phosphate concentration. So the way that we always handle the excess reactant is we say that the excess reactant left over equals the excess reactant initially minus the excess reactant that we use. So how do we get the moles of excess reactant or phosphate initially? Well, we know the concentration. That's 0.185 moles of phosphate for every liter. And we know the volume, that's 25 mils or 0.0250 liters. So this will give us the moles of phosphate initially minus what got used. Well, that depends on the limiting reactant. So we're going to start with the concentration of the limiting reactant, that 0.140 moles of calcium for every liter. And we know the volume of calcium, that's 34 milliliters or 0.0340 liters. And then we can say that for every 3 moles of calcium, 2 moles of phosphate were used. And to get the moles of phosphate initially, I got 0.00462 with an insignificant 5. Again, that's initial. Minus the phosphate used, I got 0.00317 with an insignificant 3 moles of phosphate used. So the moles left over are 0.00145 with an insignificant 2. So to get the concentration of phosphate in the final solution, just take these moles that you had left over and divide by the total volume in that final solution. Do you remember what that was? Wasn't that 59 milliliters or 0.0590 liters? And when I did the arithmetic, I got 0.0246 molar phosphate in that final solution. So I hope you get practice on problems like this. There's a worksheet with problems like this, and thanks for listening.